Welcome to the video lecture on the ratio and root tests. We discussed two tests in this section that are particularly useful for infinite series which converge rapidly. Series involving factorials, powers, roots, and infinite products are of this type. The tests typically do not work on infinite series whose general terms are rational expressions such as 1 over n, 3n plus 2 over 5n cubed minus 1, and so forth. Both of these tests allow us to conclude in certain situations that the series are absolutely convergent. This may be a stronger result than desired. If you're just checking for convergence, we will conclude absolute convergence by these tests and hence convergence by the absolute convergence theorem. Neither of these tests provide any information about the sum of the convergent series. The statements of the tests follow. So the first test is called the ratio test. And what it says is that if you have a sum from 1 to infinity of a sub n, which is a series with non-zero terms, there are three possible conclusions from the ratio test. First, the series converges absolutely if the limit as n goes to infinity of the absolute value of the nth plus 1 term divided by the nth term is less than 1. Statement 2, the sum diverges if this limit is greater than 1 or infinity. And statement 3, no conclusion about the series can be made if the limit is equal to 1. The root test has very similar conclusions. So suppose that you have the series from 1 to infinity of a sub n, which is a series with non-zero terms. The three conclusions that you get from the root test is that the series converges absolutely if the limit as n goes to infinity of the nth root of the absolute value of the nth term is less than 1. The series diverges if the limit of the nth root of the absolute value of the nth term is greater than 1 or absolute value, and no conclusion can be made if the limit is equal to 1. So the first example here, we want to use the ratio test on the series 1 over n squared and on the series 1 over n to show that the test is inconclusive when the limit is equal to 1. So if we start with the series 1 over n squared, we know that this converges because it's a p-series with p equal to 2, which is greater than 1. So we know that this is a convergent series, so let's take a look at what the ratio test would tell us. So by the ratio test, we would want to look at the limit as n goes to infinity of the absolute value of the nth plus 1 term. So the nth plus 1 term would be this formula with n plus 1 plugged in. So that would just be 1 over n plus 1 quantity squared. And then we want to divide that by the nth term, which is just this term itself, so 1 over n squared. Now when you multiply that by the reciprocal of the denominator, so if I flip this n squared over 1 over, then this is just going to become n squared over n plus 1 squared. And I can drop the absolute values because the squares are going to make this positive anyway. And the limit of this, you can see this is dominated on top by an n squared and dominated on the bottom by an n squared. So in the limit, that's just going to go to 1. So this is that inconclusive case. So by the ratio test, we wouldn't be able to conclude whether or not this is convergent or divergent. However, we know that this one is convergent because it's that p-series with p being equal to 2. So now if we look at the series 1 over n, we know already that that's a divergent series because it's harmonic. It's a p-series with p equaling 1. So what would the ratio test tell us about that? Again, we would take a look at the limit as n goes to infinity of the ratio of the nth plus 1 term. So this formula with n plus 1 plugged in. So 1 over n plus 1 divided by the nth term. And if I multiply by the reciprocal n over 1, I'm going to go ahead and drop the absolute value here because these n's are positive. So this is just n over n plus 1. And again, this is going to be dominated by that n over n, which just goes to 1. So in one case, we had a ratio test which gave us a limit of 1, which was convergent. And over here we got a ratio test where the limit was one that was divergent. So you can't make a conclusion one way or the other if that limit is 1. It could be either convergent or divergent. You'd have to pull out some other test and try to figure out whether it converges or diverges using some other technique. So let's determine if each of the following infinite series converges or diverges, and we're going to provide detailed and clear rationale for our decision. So if we take a look at this first series, n times 2/3 to the n, these are non-zero terms, our n is positive. So if we jump in with that ratio test right away, we're going to want to look at the limit as n goes to infinity of the absolute value of the nth plus 1 term. So that's this formula here with n plus 1 plugged in. So that would be n plus 1 times 2/3 to the n plus 1 divided by this nth term right here. Now to simplify this, a couple of things. First thing I'm going to do is I'm going to break up this n plus 1 power, and I'm going to take it to a 2/3 to the n and then a 2/3 to the first. When you have the same base, you get to add power. So just breaking this up like this, it's still equivalent to what we had over here. But now it enables me to see that I can cancel out my 2/3 to the n. And over here, what we're going to be left with then is just this 2/3, and then on the top of our fraction we'll have an n plus 1, and on the bottom of our fraction we'll have an n. As n goes to infinity, these two terms dominate and are going to go to 1, but it's being multiplied by that 2/3. So this is equal to 2/3, and what we need for the ratio test is that this limit, whatever it is, needs to be less than 1, which it is. So that means that this series is convergent. Okay, so recall the 3 conclusions. If it's equal to 1, it's inconclusive. If it's less than 1, it converges absolutely. And if it's greater than 1 or infinity, then it is divergent. So we were less than 1, so we were convergent. And it's actually converging absolutely, which is, stronger than what you may need in some cases. But for that first example, all of our terms are positive to begin with. So in our next example here, we've got the sum of n squared over 2 to the n. So again, all of these are going to be non-zero terms, and they're all positive as well. So if we apply our ratio test right off the bat here, what we're going to look at is the limit as n goes to infinity of our nth plus 1 term. So that would be n plus 1 squared over 2 to the n plus 1 divided by the nth term, which would be n squared over 2 to the n. So I'm going to go ahead and multiply by the reciprocal of the denominator. So I'm going to have this n plus 1 squared on top, but it's going to get multiplied by the 2 to the n when I flip this over. So I'll have a 2 to the n on top as well. And then on the bottom, I'll have this 2 to the n plus 1 and that n squared. You can drop the absolute values here if you like, because all of this is going to be positive. What I'm going to do next is break up that 2 to the n plus 1, like we did in the last example. So this will be n plus 1 squared, and I'll have that 2 to the n, and on the bottom I'm going to go ahead and move my n squared over and write this 2 to the n plus 1 as 2 to the n times 2 to the first, or just 2. So these will cancel. This goes to 1 because it'll be an n squared over an n squared, and we'll have that 2 left in the bottom. So the whole thing goes to a half, which is less than 1. So that means the series is convergent. As long as this limit exists and is less than 1, you will be convergent by the ratio test, and you're absolutely convergent. All right, the next example does alternate. It has that -1 to the power n minus 1. So this isn't always going to be positive terms. So if we go ahead and we look at our ratio test, we're going to take the limit as n goes to infinity of the absolute value of our nth plus 1 term. Now when you take the absolute value of an alternating sequence, this -1 part is going to just become +1 in that absolute value. So we essentially get to drop that part or portion of the series and just focus on the a sub n part. And we want the a sub n plus 1 term. So we're going to plug in n plus 1 here, here, and here. So this is going to be n plus 1 plus 2, and n plus 1 for that n, and then this n becomes an n plus 1 plus 1. And then we're dividing that by this original formula. So n plus 2 over n times n plus 1. So simplifying here, we're going to have n plus 3 over n plus 1 times n plus 2, and I'm going to multiply that by the reciprocal of this denominator. So when I flip this over, the n and n plus 1 go on the top, and the n plus 2 goes on the bottom. So I can cancel out some n plus 1's, and this is going to give me the limit as n goes to infinity of an n times an n plus 3 on top, and an n plus 2 quantity squared on the bottom. Now look at your dominant terms. On the top, when I FOIL this out, this is going to be dominated by an n squared. And on the bottom, when I FOIL this out, it's going to be dominated by an n squared. So in the limit, that goes to 1, which is our inconclusive case. So the ratio test doesn't work on this particular problem. It doesn't tell us whether it converges or diverges. So I'm going to go back to this original series, and because it does have that alternating piece to it, we can try the alternating series test. So let's pull that out and see if that can help me decide one way or the other. Now remember, there's two conditions that you need to check for the alternating series test. The first condition is that nth term limit. So we need to take the limit as n goes to infinity of just this portion of it. Again, you're ignoring that alternating piece. So what will be the limit of n plus 2 over n times n plus 1? Well, on top, that is dominated by the n, and on the bottom, when you FOIL this out, that's dominated by an n squared. So this is going to act like a 1 over n, and in the limit, as n gets big, this fraction gets small. So that limit is 0, and that's what you need for the first part of the alternating series test. So that's verified. The second condition that we need to show is that this series decreases. So the nth plus 1 term needs to be less than or equal to the nth term. Now you can show that in several different ways. I'm actually going to do the algebra on this to show you. So if you take your nth plus 1 term, which remember was this n plus 3 over n plus 1 times n plus 2, that's just by substituting in n plus 1 for these three n's. So this left side simplified to n plus 3 over n plus 1 times n plus 2, and we want to show that that's less than or equal to this a sub n term. Now it's not obvious to just look at this and necessarily see, because your numerators are not the same and your denominators are not the same. So I'm just going to do a little bit of algebra here. I'm going to go ahead and I'm going to cross multiply. So this left hand side is going to become an n plus 3 times an n times an n plus 1. So I'm just multiplying this way, and that's got to be less than or equal to, when I multiply this way, n plus 1 times n plus 2 squared. Now what I'm going to do is I'm going to subtract this entire right side over to the left side to get a 0. So this is less than or equal to 0. And I'm going to notice that I have a GCF that I can pull out. So if I pull out an n plus 1, then in brackets I'll have n plus 3 and n left minus n plus 2 quantity squared. And let's go ahead and FOIL that out. So I'll get an n squared plus a 3n. When I FOIL this out, I'm going to get an n squared, which will become minus from this minus. In the middle, I'll get a 4n, which will become minus because of this subtraction. And I'll get a plus 4, which becomes minus because of the subtraction. So combining my like terms there, the n squareds cancel. 3n minus 4n is negative n minus 4. And I'm going to go ahead and I'm going to factor out that negative. So I'll be left with a positive n plus 4. Now remember that n is positive because we're starting n at 1 and going to infinity. So this will be positive and this will be positive, but we're multiplying those by this negative out front. So this inequality is always true. This left side will always be negative for all n greater than or equal to 1. Since this will be positive and this will be positive, but the negative out front stays there. So this is always true, which means that this original inequality that we started with is always true for all n greater than or equal to 1. So what we've shown then is that this is true right here for all n greater than or equal to 1. So we've shown that the limit is 0, and we've shown that the series decreases. Those are the two conditions that are needed to be met in order to use the alternating series test. So we can say that by the alternating series test, the series converges, since it satisfied those two conditions. Okay, the next example here, the sum from 1 to infinity of 2n factorial over n to the 5th. Keep in mind that this ratio test is a good one to use whenever you have factorials involved, whenever you have exponents, like something raised to the n, or when you have exponential functions involved, things like that, things that are fast growing. So this one right here is a good candidate for this ratio test. So if I take a look at my ratio test, I need to take the limit as n goes to infinity of the absolute value of the nth plus 1 term. So we're going to plug in n plus 1 in for these n's. So it'll be 2n plus 1 factorial over n plus 1 to the 5th divided by the nth term. So when I multiply by the reciprocal, I'm going to get that 2n plus 1 factorial from the top here, but it's going to be multiplied by the reciprocal down here. So that n to the 5th will join it. And in the bottom, I'll have n plus 1 to the 5th times 2n factorial. Now with these factorials, keep in mind that you can break them down a little bit to do a little bit of reducing and canceling, because n plus 1 factorial is really n plus 1 times n minus 1 times n minus 2 all the way down to 1. But n times n minus 1 times n minus 2 all the way down to 1 is really the same as n factorial. So n plus 1 factorial is n plus 1 times n factorial. And that's good because that means we can cancel it with this 2n, or the n factorial from the 2n factorial that we have in the denominator. We can also cancel out our 2's, and I can cancel out one of these n plus 1 to the 5th. So this is going to go down to a 4. So what I'll have left on top is an n to the 5th, and I'll have an n plus 1 to the 4th on the bottom. So this is dominated on the top by that n to the 5th, and on the bottom by that n to the 4th, which means this is going to be acting like just an n. So as n gets big, then this limit is going to get big. So this is obviously infinity, and that was our second conclusion from the ratio test, which was the fact that this must diverge if your limit is greater than 1 or infinity. So this diverges by the ratio test. All right, the next example here is another one that alternates. We've got that negative 1 to the n minus 1, But it has exponentials and it has factorials, so that makes it a good candidate for the ratio test. So anything that has factorials, powers, roots, and infinite products are usually good candidates for the ratio or the root test. So I'm going to use the ratio test here and see if it works. If it doesn't work, then because we have that alternating piece, we could try the alternating series test as well. So the ratio test would say that we would want the limit as n goes to infinity of the absolute value, which is going to knock out this -1 part and make it become positive. So I just need to focus on this part right here, the nth plus 1 term. So when I plug in n plus 1, I'm going to get 2 to the 4 times n plus 1 over 2 to the n plus 1 factorial. And all of that is being divided by 2 to the 4n over 2n plus 1 factorial. So I'm going to multiply by the reciprocal, which is going to make this go away, and we'll get the limit as n goes to infinity of 2 to the, let's go ahead and distribute here, 4n plus 4 times this 2n plus 1 factorial from the reciprocal. And then on the bottom, I'm going to get 2n plus 2 plus 1 more, so that's 2n plus 3 factorial times this 2 to the 4n from my reciprocal. So a couple of things I want to break up here. First, let's break up this power. This is 2 to the 4n times 2 to the 4th. And then if I look at these two factorials here, the 2n plus 1 is the smaller one. So I'm going to leave that one the way it is. And I'm going to take the 2n plus 3 and break it down. The very first term would be 2n plus 3. And then with factorials, you subtract 1 each time. So the next number down would be 2n plus 2. And then if I subtract 1 again, I'm down to 2n plus 1. And that's where I'm going to stop and put my factorial symbol to account for the rest of the terms going down. And then I also have that 2 to the 4n from right here. So the 2n plus 1 factorials cancel, and the 2 to the 4n's cancel. So what I'm left with on top is that 2 to the 4th, which is just 16, and then 2n plus 3 times 2n plus 2 on the bottom. So this is just the limit as n goes to infinity of 16 over 2n plus 3 times 2n plus 2. And in the limit there, that numerator is fixed at 16, and the bottom, as n goes to infinity, is going to go to infinity. So this is going to go to 0, which is less than 1. So that's the convergent case. So that means this converges by the ratio test. And remember that it had that alternating piece in it because it had the -1 to the n minus 1. So when I say that this converges, I'm actually saying that it converges absolutely. Because when we apply the ratio test, we are taking the absolute value and ignoring that alternating piece altogether. So we showed that even if that -1 to the n minus 1 wasn't even there, it would converge. Therefore, if it has that alternating piece, it's just going to converge as well. That's that absolute convergence theorem. Now the next example here is what we would call an infinite product. It's got 2 times 4 times 6 times 8. It's multiplying all those even numbers on top. And on the bottom, we're starting at 2 and then multiplying by 5 and then by 8. So we're multiplying by, the next number is going up by 3 each time. So it's hard to kind of write out a distinct formula for this, but you can at least sort of see the pattern the way it is. When you have these infinite products like this, the ratio test works really well. So let's try it out. This is an alternating series, so if the ratio test failed, we could try the alternating series test. So the limit as n goes to infinity of the nth plus 1 term, and again we're ignoring this -1 to the n for our ratio test because we're taking the absolute value. So I'm going to take this on top and I'm going to plug in an n plus 1 right there. So this will be 2 times 4 times 6 up to 2 to the n plus 1, like that. Use parentheses there. And then on the bottom, 2 times 5 times 8 and so on. parentheses 3, parentheses n plus 1 minus 1. And then we're going to have just this whole thing on the bottom. So I'm going to multiply by the reciprocal and clean some things up. So I'm going to take all of this and I'm going to flip it over. So this will be gone. So this is going to turn into the limit as n goes to infinity of the 2 times the 4 times the 6. When I distribute this 2 across, this is going to give me 2n plus 2. And then I'm going to have all of that times this 2 times 5 times 8 times 3n minus 1. And then I have this denominator here, which is 2, 5, 8, up to, and when I distribute the 3 across, I get 3n plus 3 minus a 1. So this is 3n minus 2, or excuse me, plus 2. And then I have this denominator here, 2, 4, 6, all the way up to 2n. I'm dropping my absolute values because all of this stuff is positive. So now, if I look at these products, the 2n plus 2 product is bigger than the product that only goes up to 2n. So I'm going to break this top left product down. So this will be 2, 4, 6. These are going up by 2's each time. So the very last term is 2n plus 2. If I take 2 away from that, then the second to last number in this product would just be a 2n. So in terms of my infinite product down here in the bottom right, these terms through the 2n are going to cancel with these terms through the 2n, but I'll still have that very last number, 2n plus 2, left. Now if I do the same idea with these two guys, the smaller one is the 3n minus 1. And notice again that these numbers are going up by 3's. So the very last term in this infinite product would be that 3n plus 2. If I subtract 3 from that, 3n plus 2 minus a 3 is 3n minus a 1. So these terms through the 3n minus 1 will cancel with those. And so all I'm going to have left on top is that 2n plus 2. And on the bottom I'll have 3n plus 2. These are dominated by those two n terms, which are going to go to 2/3 in the limit. And that is less than 1, which is good news because that means we converge by the ratio test. And it was an alternating series, so this converges absolutely. Okay, so the ratio test is really good to use when you've got factorials, powers, infinite products, things like that. We haven't used the root test at all yet, and that's what we're going to do next. The root test isn't used quite as often. It's only useful, I think, when you've got things being raised to the nth power, because the root test is taking an nth root. So usually the root test is only going to simplify nicely if you've got the nth root of something to the nth power. And both of these examples have that because you've got an n up in that power. So that's how you know to try the root test. So the root test says the following. We're still taking a limit as n goes to infinity, but this time we're not taking the ratio, we're taking the root. So I'm going to take the nth root of this nth term right here. And you want to simplify that. And the nth root of something to the nth power is going to cancel out. For example, this e to the 2n, this is like e to the 2n being raised to the nth root, which is a 1 over n. And when you multiply power times power, the n's cancel, and this is just an e squared. So the numerator reduces to just an e squared because the n's cancel. The same thing will happen on the bottom because this is like an n to the n raised to a 1 over n, and when you multiply this n and this 1 over n, they cancel out to a 1. So this is just an n to the first, or an n on the bottom. So as n gets big, this denominator gets big, but the numerator is a constant because e squared is just 2.718 quantity squared. So that's fixed. And if your numerator is fixed but your denominator is getting bigger, then the whole fraction is getting small. And that's less than 1. And these have the same conclusions that the ratio test have. So if your limit exists and is less than 1, then you converge. And this converges by the root test. On this last example here, same idea. We have something being raised to the nth power, so the root test is a good choice here. We're going to take the limit as n goes to infinity of the nth root of this nth term. And this n will cancel out. So this is just going to be the limit as n goes to infinity of e to the negative 1. And e to the negative 1 is just 1 over e. And that's a constant, so the limit of a constant stays a constant. 1 over e is like 1 over almost 3, so it's about a third, which is less than 1. So that means this converges by the root test. So make sure that when you're doing these problems, we have a lot of tests now at our disposal. We've got comparison tests, integral tests, alternating series test, root test, ratio test, and I've probably forgotten some in there. So make sure that you carefully study your textbook for a summary and a strategy for testing infinite series for convergence or divergence. There is a really nice table summary of all the different tests for divergence and convergence. So look that over. Have it handy when you're doing your homework, but ultimately you are going to have all of those tests need to be memorized for your exams. Good luck. That concludes our video lecture on the ratio and root tests.